Hello, everyone, and welcome back to another episode in our Debatable Physics podcast. I hope you enjoyed our last episode on quantum computing. This week, we're joined once again by Gaurav.
Hi, everyone.
And this week, we're also joined by Mark Fuller, if you would like to introduce yourself.
Hello, my name is Mark Fuller. I work in the Department of Physics and Astronomy as the Outreach Officer. And astrobiology has been one of my interests for a long time. So I wouldn't say I'm an expert, but I definitely have a good working knowledge of all the different bits of it.
Cool. So today's topic is slightly diverging from the previous ones, as Mark has alluded to. Our topic today is going to be on whether or not there is life in other places. So that could be within our own solar system or just in the universe in general. I think a good place to start would be to consider how we actually define life. So, question to you guys, what would you say the criteria for something living is?
That's a good one. It's a tough one to start with. We learn in GCSE biology lessons all about, I think it was Mr. Grimes, isn't it? It's the different parts of aspects that make life. So you've got movement, respiration, I'll have to look up these now, growth. So there's lots of different aspects. But then there's always the classic case of fire. Fire seems to fit all of those aspects. We wouldn't consider that alive. So how does that fit into the criteria is much more difficult to define.
I was just going to say that I think defining life on Earth and defining life in the universe are going to be two vastly different definitions because, we might count like single-celled organisms, but life may have evolved quite differently in a galaxy far away. So it's quite abstract. We have to keep the definition quite abstract.
I agree completely. It's the fact that we've got one example of life, essentially, and it all comes from the same tree. If you look back at the essentially the history of life on the planet, it all seems to come from one source, which is a bit paradoxical because you would imagine that life, in all its diversity now, surely at the start would have had more possibilities. So if we're talking about a survival of the fittest issue, are we saying that all the other species died off and we're only left with this one tree of life that has this one common ancestor? That to me, that seems unlikely. However, it seems to be what we have right now. And even looking at the number of amino acids and the number of combinations of proteins you can create are astronomical. However, life seems to use very few different types of amino acids to create its fundamental building blocks. So that's another crazy thought about what happens to all the other junk. Why did life pick just those to go with? And then going even further, we're talking about carbon-based life. That's the life that we know of. You just look at any sci-fi at all. We know there's silicon-based life and all sorts of, artificial intelligence and all sorts of different methods of people have thought about how life could be. Why are we like we are on this planet? And is that the only way we should think of life?
So, coming back to what both of you guys said, like our current definition of life might be too narrow once we start exploring spaces that are outside of Earth. So the biological definition of life has like these 7 criteria that life must meet in order for it to be classified as alive. But like you said, fire is one of the things that you might think, oh, it seems to act like it's alive, but under this criteria, maybe it isn't. Another thing is viruses aren't actually considered to be alive because they don't fit all 7 of them. So, for example, they don't maintain homeostasis, so they don't self-regulate, they don't control their own internal temperature, and they don't grow either. But that's quite, I guess for me anyway, counterintuitive because it seems to do all of these things, like it reproduces, it adapts to its environment, it evolves. You would think that something like that would be alive. So maybe once we start exploring these other spaces, that's something we have to consider that not all life is going to act how we would
So
expect
going back to
it
what
to.
Mark said earlier about
That's
the
a very
amino acids,
interesting
it
fact,
might be a
given
good
the
idea
current
for us to
climate.
get a baseline
Yeah,
of how
I thought
life
it was
formed
pretty
here on
relevant.
Earth before we start discussing if it formed in other places. So Gaurav, if you would like to talk a bit about that.
I'd be happy to. So my explanation is going to be very simplistic, based on my knowledge from GCSE biology. So first, it's essential to know the building blocks of life, and as Mark mentioned, these are the chemical compounds, the amino acids, and the most common ones are hydrogen, carbon dioxide, phosphate, nitrogen, methane, and ammonia. And for these compounds to react with each other, they need to be in water. So the first life forms began in the ocean. To be precise, the ocean floor, where they were shielded from UV radiation from the sun. And because they needed an energy source, like plants do from the sun, they used the hydrothermal vents on the ocean floor. Now, these are basically cracks in the Earth's crust that allow heat to escape from the Earth's core and mantle. The water that comes out of these vents also contains some other rich minerals, and together with these chemical compounds, they're called primordial soup. This then led to the first life on Earth, called the last common universal ancestor, or LUCA. And from LUCA, the most basic microorganisms evolved, and they created more complex sea organisms who then eventually migrated onto land, and from then to humans, if we gloss over the mountain of complexity that it took to reach humans in the evolution change. Now, it's estimated that these first life forms formed around 4.28 billion years ago. Thanks, Wikipedia.
I think it's important that we realise that this happened a long time ago, and the conditions that the Earth was in during this time was different to today. So a lot of it is guesswork. It still is. I mean, we make very good estimates, and as scientists, we eliminate probabilities and we try and make the best estimate of what we think it was like. But there's all sorts of different things out there, and there's all sorts of different possibilities that we would overlook. Again, because we're looking at it from how we see life now, and then we're sort of going backwards. Whereas, in fact, if you did it the other way round, a bottom-up approach, we might see completely different things forming. I mean, DNA, for example, the formation of DNA, again, seems to be this common thing through life. Now, I'm no expert, but there's all sorts of. We talk about viruses. So viruses, again, RNA is important in how a lot of simpler organisms function, and obviously key to how DNA replicates. So, where was those developments, and what happened in what order? Was RNA first before DNA? How did the DNA formulate its simple four-base structure? Did we have different forms of life before that were too complicated and died out? Did we have a start, conditions changed, it got wiped out, and start again? We're talking about a Noah's Ark type situation here where, you wipe out most of the planet again. And again, we've had conditions, and we know we've had these mass extinction events before. So how long did it take for life, and did we have some false starts before we got to this tree of life that we have now?
I absolutely agree. We have absolutely no evidence or even fossils of LUCA. So again, this is all just guesswork. And like you said, there could be a number of possibilities from which life could have started. I mean, like you're saying, if we go from the bottom-up approach, then really life is purely based on chance. It was just a chance that our life today evolved by going down a certain route. And if there were different conditions, life today as we know it could be absolutely completely different, and maybe even unrecognizable.
So if we put that aside for a second and we just assume that, okay, this is exactly how it happened, this is exactly how life evolved here on Earth, How likely do you think this process would be to happen in other places?
Again, it's incredibly difficult because we only know of one example. This is our big problem, and I think one of the reasons of getting out into our own backyard in our own solar system, if we discover life on another planet, if we can discover very simple bacterial life or whatever on Mars, we've got the certain satellites in around Saturn and Jupiter that could potentially have conditions similar enough to Earth at some point in their lifespan to support life. Now, whether that's life now or fossilized life from a previous mass extinction event, essentially, that will give us a new perspective. That will start opening our eyes to things that are outside of our own very local neighborhood, outside our own biosystem, essentially. But even looking on Earth, we get these extremophiles. We get these creatures that shouldn't be able to exist. I mean, they are living in such hostile conditions that under any normal conditions, they should not be able to. Extremes of temperature, extremes of pressure, lacks of oxygen. There's so many conditions that make these things unlikely that life seems to be able to thrive. Where on Earth, wherever we look, we are finding life. Whether it's in Antarctica, if we're talking about deep sea vents, we're talking about all sorts of places where it will seem extremely unlikely for life to be. We're finding it. Now that seems to suggest to me that life is extremely versatile and can adapt. However, can it start? And that's the interesting point. Can it start in a hostile environment? Or does it need very, very stable conditions in order for it to start in the first place? And that's the big question.
I think an interesting thing to think about is that these extreme conditions that we classify are very human-centered. So maybe in other planets, in other solar systems, these extreme conditions are the normal. And if there are life forms that have developed in these hostile conditions, it's their normal, but it's a hostile condition for us, maybe. So I'm not really sure how we can define for life to form and not to sort of give it a general definition from life on Earth, what is a hostile condition. And I was going to say, for the process of life, the process in which life occurred on Earth, for it to occur outside of our solar system, I feel like would be very, very unlikely, given that there have been so many events in the Earth's history that have led to life being developed the way it has on Earth, as in it's very, I think, unique, even in our universe. So maybe there might have been other processes, and I feel like given the vast scale of the universe, even if life has a very, 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 very small chance of developing, then that would still mean there's there is many chances for life to develop in ways that we might have not even thought about.
I agree that there are a lot of conditions on Earth. I mean, the fact that we have a relatively large natural satellite, the moon, so close to us, and it's creating tides, stabilizing orbits, stabilizing the whole situation is really interesting. The fact that we've got Jupiter out there, which is sucking up all these asteroids that could have been flung our way and potentially destroyed life many times over. You just have to look back at Shoemaker-Levy 9, and we've actually seen it's happening. It's still happening today. And in the early solar system, we know it was a lot more dynamic. There are a lot more of these asteroids and meteorites flying around, bashing into planets. We can see the evidence of it on the moon. We can see evidence on other planets. The only reason why we can't see evidence on Earth is partially because of life, because it's been covered over. We've got all these dynamic effects. We've got weathering systems. We've got all this stuff that's actually, destroying all the evidence of these large impact craters. But we still know there's places that are more remote in deserts where there isn't so much of these situations happening, where you see these big craters still. And going right back to the evidence of potentially of the dinosaurs being wiped out by a huge meteorite. we can see sort of evidence of where that might have landed. And that's what's wonderful about science. You can make a hypothesis and then search for the evidence and actually see how well they line up. And once you can do that, you can refer back and iterate and make better predictions on what you're actually learning.
That's actually a very interesting point about like the certain conditions that Earth needed for life here. So I think the very like active period you were talking about is called the late heavy bombardment, and that's a period in Earth's history where it was really young and it was just being bombarded by these bodies that were around in the solar system at the time. And the time that this happened actually slightly overlaps with when we believe life had started in the universe. Oh, sorry, I mean here on Earth. And that leads to alternative theories as well about how life started, because some scientists believe that if life was around or alive during this time, it would have been wiped out during this period in Earth's history because the conditions were just so hostile that no life would have been able to survive. However, there's also another idea of life actually being brought to Earth on one of these many bodies that impacted, and it's called Panspermia. So this is the idea that life may have originated somewhere else in the solar system, and it was on one of these rocks that just happened to land here on Earth, and that's how we got life.
I was going to say that if life has come from somewhere else in our galaxy or the universe, then that means that life form might either still be out there or may become extinct. So that obviously points to the fact that either we are not alone right now, or at some point in Earth's history we haven't been alone. So again, I feel like for the life form to have traveled all this like distance, I mean, given that we are like carbon based, we need oxygen, plants need carbon dioxide, they obviously would have not had access to that. So maybe in some point the way that life form that came to us on an asteroid, for example, operated, who basically lived, would be different to how we basically live, I think.
The panspermia idea is really fascinating, and I think, again, it goes back to looking at life in our solar system. One way of sort of getting the evidence for that is actually seeing if there is there a common ancestor to potentially life on Mars, on natural satellites Europa, things like that. If they all seem to have a common ancestor, then that suggests that it wasn't born on Earth but elsewhere, and came into our solar system, or came from one of those bodies in the solar system and spread out from there. That's an interesting possibility, and I think, again, if we can discover a common ancestor on different planets, on different ecosystems, that would be incredibly interesting, and that would suggest that there has been some sort of seeding from external onto our planets. Now, I'm not saying that is, when I say seeding, I don't mean it has been done by some sort of alien civilization going out there and saying, yes, let's scatter some civilizations around the universe. I'm not saying that's impossible, but I'm not suggesting that's the only way of doing it. But these natural meteor impacts, they could have contained all the right building blocks for life, all those amino acids that we spoke about, and it just happened out of thousands, millions of collisions, that one of them just hit the right point, had the right chemical balance on board, created the right conditions at that specific moment to create this life, to create this very, very basic building blocks. And that, I think, is personally, I think that is one of the most likely forms of how this might have happened.
So that makes it seem as if all of the processes
all the building blocks in one package,
to life
and it just
forming
being the
on
right
Earth
time
were
and the right place
just pure
for that to happen.
coincidence, and there was just a lot of luck involved with having the right conditions and it happening at the right time. This kind of leads into the Anthropic Principle. Would you be able to explain that a little bit more, Mark?
So the Anthropic Principle is that when we look at the universe, particularly from our perspective as humankind, it seems quite tuned to allow life to happen. We have, again, if we look in we've discussed already, if we look in our local system, we've got a nice star that has got a nice long lifespan. When I say nice long lifespan, we're talking sort of 10 billion years, which is pretty good. It gives you enough time for life to develop, maybe stutter, maybe get extinct, start up again. It gives us all those possibilities that we've discussed. Now, if stars only lasted 1 billion years, then is it likely that life will get to the point where it will be intelligent life? Is it likely we'll get to the point where we can actually say, oh, there's not only bacterial life on here, but something bigger than that, something that we can communicate with, something we can talk to? And I think that's what most people think. When they think of aliens, that's the thing that most people think about, the people like us, or things like us, that can think and communicate. They're the ones we want to talk to. So the Anthropic Principle says, okay, the universe is to be tuned. And in fact, even things like big G, the gravitational constant, if that was slightly different, then stars would have a different lifespan, and stars would live a lot shorter lives, or potentially not even form at all, because there just wouldn't be enough gravity pulling these massive clouds of gas together, and we'd just have things like brown dwarfs. They wouldn't get any bigger than that. So the universe appears to be tuned for life. Now that gives us an interesting dilemma. So it either suggests there is some sort of higher functioning here that makes the universe want to create life. There's something out there that says, okay, we really want this to be life. Now that's the very strong version of it, that the universe is life. The universe wants life. The universe is tuned for life. That's what we have. Now, there's the weak version of it, which sort of says, well, of course the universe appears to be tuned for life like us. We're living in this universe. So the fact that we're living here and we can look out and we can see the universe, then naturally it's going to be tuned for our type of life. Now, we can talk about quantum mechanics, and we can talk about multi-universe theory and all sorts of things like that. And maybe there's lots of different universes out there that tune for different types of life. Now, again, that's a intriguing possibility. But once again, it's another constraint upon intelligent life. It's another constraint upon life in total. So it's another thing to think about when the universe, even the whole universe, appears to be for us, for life.
Yeah, that's actually really interesting to think about it that way. I was just going to maybe come at it from like another viewpoint, and in the wise words of Albert Einstein, everything is relative. So you've defined that obviously stars are have a lifespan of 10 billion years, and that is enough for life to form. But for all we know, even 1 billion years might be enough, or even 10 million. We just don't know. I mean, I think putting constraints on the conditions on which life can form, I mean, we just don't know. Like, life may thrive in places that we don't know. Like we see on Earth here, maybe they can thrive in completely different systems across the universe. But obviously, if we're saying that the universe is tuned for our life, then we're talking about our life specifically. Now, I'm not sure if that means that there will be similar life across the universe, similar to us, or they would be vastly different to us.
I think this links back to what Mark said earlier, and the fact that we only have this one case study. We only have Earth, and we're trying to extrapolate all of this information from this one data point, basically, that we have. And that's very difficult to do. So a lot of the kinds of things that we are talking about, they are just speculation and us thinking outside the box. Yeah, so I guess the next
one
point
of the
from
ways
this
that
is,
we try to quantify the number of civilizations
that
we might actually be able
how
to
do we
communicate
go
with
about actually trying
is
to
by
search
looking
for
at
these
the
life
Drake
forms?
equation. This equation defines a set of parameters starting from the rate of formation of stars in our galaxy, and then going on to more strict criteria. So, for example, how many of those stars have planets, how many of those planets are habitable, and how many of them would be able to support life. And we go down this set of criteria, and eventually we reach a number that defines how many civilizations we think that we could communicate with.
The thing is, the Drake equation is come from SETI. It's come from the Search for Extraterrestrial Intelligence. It was in the 1960s, 1961, I think it was. Frank Drake came up with this idea of trying to quantify our search for this extraterrestrial life. It's been put down. People have said, oh, it's far too simplistic, and different people, if you look at the different conditions, different people can say, well, the universe should be teeming with life, or the universe, the galaxy even, should have very little life in it, or the galaxy should be teeming with life. And depending on the conditions you put in, very much depends on the answer you get. So it's not an equation. It is as a guide at best. The best way to use it is to sort of look at what we don't know. There's so many terms that we don't yet know enough about, particularly towards the end of the Drake equation, that you can actually sort of start putting constraints upon and start looking for evidence for and start researching bits about these things. So it gives you a guide of where to look for this information, which before the Drake equation, we sort of were just in the dark, really. So I really like that perspective, and you can see how much it's changed. I mean, originally when Frank Drake put the equation together, he said each one was basically a tenth. So there's a 10th chance of a star being stable enough to support life, to have planetary bodies around it. There's a 10th chance of there being planetary bodies about it. There's a 10th chance of there being one inside the habitable zone, so the area where liquid water could exist. Now, we can talk whether liquid water is essential for life or not. You can go around in circles for a long time. But those questions, by asking those questions, you start looking at where you need to look next. And you start saying, okay, so we don't know enough about this. Let's look further into it. And that's where the Drake equation is really, really powerful. And it works throughout not only the astronomy and physics side of it, but into the sociology side as well. And so there's great discussions you can have based on elements of this Drake equation and what your personal beliefs are, and you can have some great discussions, sort of like we're having now, about what the chances of life actually existing are. One thing I should say about the Drake equation is it's not representing how much life there is in the universe. It's not even mentioning how much life there is in the galaxy. It's saying, what is the chance of us finding a civilization that we can communicate with? So again, even that is putting quite big constraints on what it's trying to achieve.
So just to quantify this slightly, if we take an optimistic case of the Drake equation and set all of the parameters to 1, and then we say that the average lifetime of a technological civilization is about 1,000 years, we would get an average number of civilizations that we could communicate with as 1,000. So that's quite a large number of civilizations. But on the other end, if we take the pessimistic case, so there's also some case studies done of like very pessimistic cases of the Drake equation that yield a number of about 10 to the minus 14 number of civilizations. So you can see just the range of values we're working with. So like Mark said, it's not really an equation, it's more a guide for us to then use and go forward with as we continue our search for life.
My thoughts on the Drake equation are, I absolutely agree with you. There are so many unknown possibilities to this equation that makes it so interesting and profound. And like I mentioned before, maybe our computing intelligence, artificial intelligence, will definitely help us to explore and maybe even communicate with other life forms out there, because obviously we're searching for life forms that we can communicate with, but maybe there are life forms out there that can communicate with computers and artificial intelligence that we might not have been able to communicate with. So that's obviously something interesting to think about, because obviously our perception of the universe is, for example, it's a 4D universe for us. There might be other life forms out there that exist in multiple dimensions, and for that reason we can't communicate with them. They might be, for all we know, living on Mars, but we can't exactly see them. And obviously with computing, maybe we might discover things that we might have not discovered without the use of computers in our very human-centric sort of viewpoint of life.
I think the communication angle is really interesting because you look at, I mean, we've been broadcasting for the last sort of 100 years. We've been using radio waves, powerful enough that they can be seen sort of outside our atmosphere for approximately 100 years. It's not that long. I mean, it's compared to the whole length of human civilization, it's tiny. But then you look even more specific. I mean, look at, Wi-Fi standards change like once every 5 years. I mean, so it's like a civilization that like ours, that does communicate a lot with itself, is creating all this traffic, is creating all this information all the time. Now, you've got to assume two things. One, that all civilizations are like that, and there's no guarantee why. And two, that they're using the technology that we can detect, and vice versa. So there's been a whole lot, SETI have done an awful lot of work on thinking about what's the most fundamental thing you can look for. And one of them is the 21 centimeter wavelength, the hydrogen wavelength, 21 centimeters, because it's everywhere in the universe. It's the most common material in the universe. So therefore, can we use that as a base guide? Now, again, it's a nice idea, but again, it's a human thought. It's a way that we think about things, and it assumes things that we think about. Maybe you could do it the other way around. You could say, what's the rarest thing? What's the most unique thing you can find? Let's try and communicate using that. So it depends so much on who we are. And the question is about, so we're now talking about communication. We're now talking about reaching out to civilizations that we probably will never be able to visit, not without giant leaps in technology. The distances between these potential civilizations is so huge that the only way you can communicate is one way. You can send a message out and wait 50, 100, 150, 200 years and then receive something back. It's going to be a very, very frustrating telephone call, waiting for your reply to come back. But that's the way we're looking. So we're listening for those messages. We're listening for things that have been sending out a communication for millennia, because that's how long it's going to take to get to us. But essentially, we're quite scared of sending signals out because we're worried what might come back. Now, maybe all civilizations are like that. So if we're just a group of civilizations just listening, and no one's broadcasting, then actually we're in trouble because we wouldn't see it if it was right on our doorstep. But if everyone's just listening and no one's actually talking, so that's one of the potential issues about communicating. Something I did want to say, going back to looking for life in our solar system, I think it is important and incredibly important. And I think this was considered very important in the early days of space travel, and I think we've lost it a little bit. To making sure that we're not contaminating, to make sure that when we're visiting the moon, Mars, etc., we're not bringing any earthbound viruses, whatever it is, with us. There was a recent, I think it was an Israeli mission that fired some tardigrades. They had a little container of these little, they're called water bears, these little things. And they're very good at things like hibernating. They're almost on that extremophile element. They've got very long lifespans in a hibernated state where it's very bad conditions for them. And then when conditions are good again, they can thrive. Now they've launched this mission with some tardigrades on it, and it's crashed into the moon, and now they don't know where it is. So essentially, we have now just seeded another planet with some potential life organisms, and that to me is a massive warning sign. If we're going to be quite slapdash about sending things out into space and not making sure they're fully decontaminated and fully prepared for searching for life rather than planting life somewhere else, I think we're going to end up potentially wiping out whole civilizations. We've done it before. I mean, when we've got across to the Americas, we took all smallpox and everything with us. Could we potentially be wiping out very fragile ecosystems on other planets while we're trying to search for these things? It's something we've really got to consider. And I think with the age of particularly commercial space travel, where it's becoming easier and easier to launch things into space and potentially launch probes to other planets, are we in danger of wiping out things before we even just find them? And that's quite a scary thought. So I think we've got to work a lot better on international treaties to make sure that what we're doing is safe and secure and scientifically valid.
That's a really interesting point. not just because it might wipe out like current extant life, but also because now if we go to the moon, for example, and we find evidence for life, we can't necessarily be sure whether it was because it was originally there or because we contaminated the moon's surface. And yeah, it's a very important thing for like all of these space companies to be thinking about.
Yeah, that's a really interesting thought. It almost sounds like there's a conflict in science of whether, don't contaminate outer space and because we want to search for other life forms out there, but also at the same time you have people in science looking at colonizing Mars or other planets, and in those cases there's absolutely no way we can't not contaminate other planets out there. So it almost seems like there's a debate of whether or not we should expand our civilization to other planets, or almost as if stay here and look for other life forms out there instead.
It's a nice thought that it's quite a looped thought, but going back to the panspermia theory, maybe we were just a space mission that left behind some bacteria, and that's where we came from.
A space mission gone wrong. But yeah, I guess we've spoken about the idea that we're basically listening for these other civilizations to try and communicate with us. But what if they are actively trying not to communicate with us because we're just so low down on the hierarchy of civilizations that we are basically like bacteria for them, and we're just not on the same level as them, and they can't be bothered to deal with us or give us their time of day. So there's a very good gesagt video on different levels of civilization, basically, where you have type 1 civilizations that are able to harness all of the available energy on their own planet, type 2 that can harness them in their own planetary system, type 3 within their own galaxy, type 4 within multiple galaxies. And on that scale, we are not even a type 1 civilization. We're about a 0.7 civilization. So if we're using that logic, then yeah, in the grand scheme of things, we might think that we are very intelligent forms of life, but I guess maybe not.
I mean, that's an interesting metric to think about as well. I was just going to add to that, there's another also interesting metric for measuring intelligence, and feel free to cut this bit out because I've been talking about this book for the past 2 episodes, but I just find it really interesting. For some reason it fits into everything. But the book called by, Life 3.0 by Max Tegmark, the title of the book, Life 3.0, pertains to this scale. The first bit is Life 1.0. And those are stuff like bacteria and animals who evolve through reproduction, but they do not evolve in their own kind of life. For example, a bacteria has one and only one goal, and that's to go out there and reproduce. Now, in its lifetime, it doesn't think to itself, oh, maybe I can do this or do something else. It only has one and only one goal, and that is Life 1.0. And then there is Life 2.0, which is us. We not only do we evolve through evolution, but we evolve in our lifetimes. We're not obviously pertained to like one specific goal. We have our own consciousness to do whatever the hell we want. And then there is Life 3.0. Whatever they learn in their lifetime, they then pass on to their children, for example. We can't do that, obviously, because we have to learn language, maths, etc. from scratch. Yeah, again, that's like an interesting thing to think about, and maybe that's something that's universal to life across the universe.
Yeah, it's one of the many powerful things of machine learning, the idea that you can not only pass on your genetics, your program, if you will, but you can also pass on all the things you've learned as well. And human beings are very inefficient at doing this. We have to go to school, we go to university, we do all this, we have discussions like this. That's the way we pass the information. A very inefficient method. Is there a better way of doing that? And if so, does that make life that does that much harder to communicate with? Is it going to be impossible for us to even conceptualize what's going on there? They won't necessarily need the spoken word. There could be other forms of communication which are much more efficient to them. So that's going to make it harder to communicate. Going right back to the starting point. Okay. I think a good question to think about is, should we care? Does it matter? We've just mentioned that life on this planet is a 0.7. You know, we are not even harnessing all our potential on this planet. Should we really be going out there and going, oh, let's look at other planets. Let's get this planet sorted out first. Let's get the problems on this planet solved. Let's make sure we don't destroy ourselves before we start going out there and start communicating with other civilizations. Now, the counter argument to that is, and the one I hope, is that if we do find life out there, it's going to be a unifying force. It's going to be something that says, actually, we're not alone. There is a bigger picture out there, and we're part of a bigger universe. We're part of a bigger galaxy. Which one, how it happens, again, science fiction has answers both ways. One that we turn on ourselves and this alien civilization comes in and destroys us all, or vice versa. So yeah, there's problems with humankind. Shouldn't we be solving them before we start worrying about elsewhere?
I think my opinion on that is the fact that we don't know the benefits. So like you said, it could be a unifying force. But even if we find life elsewhere and the actual impact of the life isn't major on us here on Earth, just the process and the journey of trying to find that life could yield so many things. So for example, space travel, a lot of people have the same argument where they're like, what is the point? We have so many problems here on Earth. We could be using those same resources and trying to fix the problems here on Earth. But they don't realize all of the technological advances that space travel has brought that make their daily lives so much easier. So I think you could use that argument to say we don't know how beneficial this search for life could be until we do it. And in that case, isn't it worth trying?
I was going to say, you've basically stolen what I was going to say. Yeah, I completely agree with you. It's a very philosophical question. And there are, of course, people out there who feel like funding and money to sciences should be diverted to helping, like, now, the short term. But it's really important that we also invest in the long term. And, for example, why are we looking at, why do we care about understanding the start of the universe? Well, maybe because it might help us with today. And like you said, maybe looking for other life forms out there, even if we don't find any life at all, that's completely fine, because in our search for finding other life forms out there, we might better understand our life here on Earth, and it might help us with today's problems. Of course, we just don't know how.
So, one final question for you guys. What is your final verdict? Do you personally believe there is life outside of Earth somewhere else in the universe?
From my perspective, looking at all the diversity of life on Earth that we have here, and the way it can adapt so easily to different environments, I find it very difficult to believe that we won't find life on another body in this solar system. I really do think there is going to be life on some other body in the solar system, and we will discover it within the next 50 years, is my guess. Hopefully sooner. Going wider, is there life further than that? Is there intelligent life further than that? That is where I start stumbling. And that is where I start thinking, actually, I'm not sure if there necessarily will be ever a civilization we communicate with. Even one way, even because the lifetimes of civilizations appear to be too short. For the amount of space, for the amount of distances out there, we're very, very bad at destroying what we've got. And again, this is a very human-centric way of doing it. But I think if any civilization is going to go through the way of being able to communicate outside of its own planet, I think it has to go through those procedures. It has to go through a sort of an industrial revolution. It has to go through a technological revolution. All those things need to take place. And from our own history, and I'm not just talking about modern history, I'm talking about the Mayan civilization, Roman civilizations, they seem to have a very short lifespan. And then we go back into a period of dark ages, and then we start again, almost. I worry that extinction events are too common, whether or not they are natural, a meteorite strike, or made by that intelligent civilization. I think they're so common that actually finding intelligent life again out there that we can communicate with is going to be extremely tall order.
I was going to say, I do. I definitely feel like, going back to the Fermi paradox and like running through the numbers in my head, there's got to be life out there. And by not saying that the life out there should be this, it should be that, it should breathe, it should be very human-centric. I feel like there could be any life out there if we don't put any constraints on what life should be then. So yeah, I completely agree. I feel like there is life out there. We just don't know how to communicate with it, or it's too far away.
We hope you enjoyed listening to us today. Once again, everything we have expressed is our own opinion, and we don't claim to be experts in everything, although Mark may beg to differ. So forgive us if we have made any mistakes, whether that's technical or just otherwise. I will link references and extra resources in the description box below if this is a topic that interests you and you want to do further research. And that's bye from us now. Bye.
Bye.
Bye.